All right. Hi, and welcome to the re-recording of Recitation 1. Just give me a second to get my screencast here going, and we'll dive into yesterday's recitation material. Okay. Here we go. All right. So like I said yesterday, we're working on sections 1.5 and 1.6 for this week's worth of material, working on limits specifically and how to evaluate those limits, whether it be graphically or algebraically. So we've got two kinds basically that we're looking at. We've got finite limits and infinite limits. And so by that, I mean your limit, you either find a number for it, typically an integer, can be a fraction, could be something like that, or you would find that your limit tends towards infinity. At this point, we have not evaluated limits as x tends towards infinity, only where the limit itself is infinity or negative infinity, but we will probably touch on that soon. But to start, we're just going to start with a graphical representation of limits that have finite answers. And I do want to say that sometimes limits just don't exist. There is no finite answer, and we'll touch on that today as well. So number 4 from the textbook, section 1.5, state the value of each quantity if it exists. Also in the instructions for this question is to explain why it does not exist, which I will do. So to start, we have the limit as x tends to 2 from the left. You'll see in my recitation note that I send out that I put this in quotations. It's very important to think these problems in English as to actually attach meaning to them, because for a lot of people, these symbols are new and they might not click right away. So it's very beneficial to kind of think them out, how you would say them, how you would, if we were in an actual class together, if I were to speak it to you, it would be the limit as x tends to 2 from the left. And the negative signifies from the left because by standard convention, we've assigned the left half of the x-axis to be negative, and by standard convention, the right side is positive. So when you see negative, it means from the left, positive, it means from the right. For this particular one, the limit as x tends to 2 from the left. We're going to look at the left half of this function. It's clearly a piecewise function with some discontinuity. We haven't really defined what discontinuity is, but if a function's discontinuous, like for example, at this point here, there's a jump there. It's pretty clear that it's discontinuous. And we're going to be looking at these points of discontinuity to evaluate these limits here. So if we're looking at coming on the x-axis from the left, then we're looking at this aspect of the function here. And as we get closer and closer to 2, what is the limit? What is the function value in this case? And the answer to this question is 3. We will see that the function value and the limit from the left and the limit from the right are all closely related, specifically when we get more into the criteria for continuity, which if I had to guess, would be next week. But suffice to say that for this question, for the limit as x tends to 2 from the left, it's just the function value. It's just f of 3. So now as we address x tends to 2 from the right, we look at the right aspect of the function. And while I do recognize that we're kind of breezing over this hole here, we're not concerned with it at this point. We can, maybe if I draw my arrow a little better to be more representative, we're really only concerned with this hole here. And yes, they are called holes where there is a lack of function value. Technically, the function value does exist at the point f of 2. The function value at f of 2 is 3. But as we're evaluating the limit from the right, we find that the limit here is 1. Right there. Okay, now we talk about the limit as x tends to 2, not from the left, not from the right, but in its entirety, what is the limit as x tends to 2? And this is the part that the question was asking us to explain. Basically, one of the biggest takeaways that you want to take away from this recitation is that if the limit from the left does not equal the limit from the right, then the limit does not exist. And that is the answer to this question here. And you'll often see it does not exist abbreviated as DNE. And since the limit from the left does not equal the limit from the right, you cannot use an equation symbol. So we do use equation symbols we'll do a problem later where we're asked about asymptotes, and I'll say that x is equal to, and then I will do a few integers with commas. That is different when I say that you can't have something equal to 2 things, because I'm abbreviating when I say x is equal to 2, 3, 4. I'm saying that x is equal to all of those things independently, but rather than writing them out separately, I'm going to put them in comma in list form and set them all equal to x. That's an abbreviation. When I'm talking about whether or not something can actually equal two things, the limit cannot be both 3 and 1. We've just determined that the limit from the left is 3 and the limit from the right is 1. And so the limit as a whole at x is equal to 2 does not exist. And we'll get more into that when we address criteria for discontinuity and things like that more next week. But you should know that if the limit from the left is not equal to the limit from the right, and this is written in my recitation lesson plan, that the limit itself does not exist. And DNE is a perfectly fine answer. I know that it doesn't look great to have an equal sign next to does not exist. That's just the way that I ended up writing it on this. If you are given an exam question and it says the limit is x tends to 2 of f of x, and then they also write in the equation symbol, the equal sign, excuse me, that does not mean that you have to come up with a finite answer. If Dr. Zielecki were to give the question that way on a quiz or an exam where the equation symbol is already written, that doesn't necessarily mean that you have to come up with a finite answer. Does not exist is always a possible answer for these questions. Excuse me. Okay. All right, moving on to f of 2 below the graph. So we're just asked to evaluate the function value. Like I said, the function value at this point is 3, and we see that the limit from the left is equal to the function value. It's obviously not 1 because there's a hole there. It's meant to signify that there is no function value and that the function jumps and the function value is associated with the left half of the graph. So now we address the limit as x tends to 4. Since it's basically the same from the left and the right, my best guess is that because they're the same, that's why they didn't ask you to do from the left, from the right, and then to determine whether or not the limit exists. Because it's the same from the left and the right. You have that one hole. So it's kind of obvious to say that the limit here is equal to 4. Now, f of 4 does not exist. There's a hole there. The function does not have a value at f or at x is equal to 4. And this might seem a bit abstract, and it is, and it's because these piecewise functions with these holes and these discontinuities, they're designed specifically to test your skills in determining limits. So this is not what a typical graph looks like, as we're aware. This is not what a natural graph looks like. Like a parabola would never have just a hole for no reason, but these graphs and these questions are engineered specifically to test your understanding of limits and how to evaluate them. Okay, moving on to number 5. State the value of each quantity if it exists. Like with the previous question, number 4, it also asks us to explain if it does not. So the limit as x tends to 1. So you've heard me mention how the function value and the limits are closely related. More often than not, in natural functions, the limit is the function value. When they ask you to evaluate the limit at the point x equal to a, f of a in a normal natural function without discontinuities and things like that will be the function value. You just plug in a into the function. And so when we're asked to evaluate the limit at x is equal to 1 here, it's just this function value that corresponds. And I did doodle this myself, so it's not super accurate, but it is meant to be 2 there. The limit as x tends to 1, what does it stop at? 2. So now the limit as x tends to 3 from the right. Same kind of deal that we just talked about with the last problem. So we're going to address the right aspect of the function, and we notice that it's approaching this hole here. And so what is the limit? 4. We always answer these. So it's not as simple as saying that it's equal to a function value, a limit. It's not as simple to say that the limit as x tends to something is equal to the function value of that something always. But that is kind of the general pattern. You'll see that the x tends to is what you plug in, and then what you're going to find is the output, the function value, and that's what it's supposed to be equal to. Then we get into the realm of discontinuity and whether or not it's even possible for the limit statement to be equal to that value. But in general, for simple equations, the limit at x is equal to a is going to be equal to f of a. So now looking at the limit as x tends to 3 from the right. So I clearly just did that backwards. So the limit as x tends to 3 from the right is 4. I addressed the right aspect of the function first. Like I said, standard convention. So if we are addressing it from the left, as I should have done previously, the function value is going to be 1 there. Or not the function value, excuse me, there's a hole. The limit is 1. Okay, so now the limit as x tends to 3. Like we discussed before, if the limit from the left is not equal to the limit from the right, then the limit itself cannot exist. And so we say that the limit as x tends to 3 of f of x does not exist. And I also want to say that since these are my own doodles, I didn't outright label this function as f of x. When you're given these problems, they'll be set up very clearly so you know what is to be labeled what. So you won't just be arbitrary. I won't just throw out f of x if I don't tell you what f of x is. And by I mean an exam. If Dr. Zalecki were giving you an exam, he would make all aspects of the question very explicit and very clear. But since these are my own notes, I just kind of doodled it myself. You can assume that the red graph is f of x in this case. All right, so the function value, f of 3. We see that the limit from the left is 1 and that the limit from the right is 4, but neither of those are equal to the function value. We just have a floating point there at f of 3, and it's equal to 3. Okay, moving on to number 9. So the limit as x tends to negative 7, excuse me. So this is where we're getting into limits that are equal to infinity or negative infinity. And you should be able to recognize from your algebra prerequisite experience that this is an asymptote. There isn't a whole lot that you need to know about asymptotes in the scope of this course. I think I mentioned in recitation that beyond limits, it'll probably only be brought up towards the end of the semester when we do these all-encompassing problems that are meant to drudge up all of the things that you've learned throughout the semester. But asymptotes are simple enough that you should have a grasp of them. And the last question here is about asymptotes. So aside from being able to identify an asymptote, which you should be able to see that if these two aspects of the function are both delving down towards negative infinity and they're approaching that same vertical line, that there should be an asymptote at x is equal to negative 7. So I'll go ahead and I'll write that in, x is equal to negative 7. So like I said earlier, when I was talking about how limits cannot be equal to two things and have a limit. So if the limit from the left is not equal to the limit from the right, you can't say that the limit itself exists because the limit cannot be equal to two things. This is that kind of abbreviation I was talking about where I'll just write them out in list form. So we clearly see an asymptote at x is equal to negative 7. We also have one at negative 3 and at 0 and at 6. So that was the distinction that I was talking about earlier. So the limit as x tends to negative 7 of f of x. Like I said, it's plunging downward towards negative infinity. And so the limit is negative infinity. And like I said earlier, it might not look all that pleasing to have something equal to does not exist, DNE. Even less so, I think, to have something equal to infinity because it's infinite. How can you say it's equal to anything if it can never be reached? But when we're doing these problems, that is correct. The limit is negative infinity. And just by nomenclature, that's usually how we write it out, that it's equal to negative infinity, even though nothing can ever equal infinity or negative infinity. So the limit as x tends to negative 3. You probably guessed, it's positive infinity. The limit as x tends to 6, we'll come to that one in a second. Limit as x tends to 0. So this one again, positive infinity. Now the limit as x tends to 6. So we have it from the left and we have it from the right. And clearly one is going down towards negative infinity, one's going towards positive infinity. So we're coming from the left here and we end up going down. So the limit as x tends to 6 from the left is negative infinity. And then same sort of deal, coming from the right, we see the function coming up towards the side of the asymptote, but going up towards positive infinity. And so the limit as x tends to 6 from the right is positive infinity. And like we said, it asks us to find the equations of the vertical asymptotes. If it's not obvious to you that that the equation for this particular vertical asymptote is x equals to negative 7, this is the x-axis. And what's a line that intersects the x-axis going to be equal to? It's going to be equal to its intercept, because at all points it's going to, because at all points it's a vertical line. It's going to be equal to -7. So x equal to -7, x equal to -3, 0, 6. That's how you write out what an asymptote is. You won't typically be asked to determine asymptotes. I think that this problem was probably included just to get you thinking about your prerequisites. Like I said, it's not like we're never gonna talk about it, but it's not gonna be one of the biggest parts of this course. So moving on to the next one. So these are the algebraic representations of limits that I was talking about earlier as it pertains to infinite limits. And these ones are a little bit more difficult to explain. And so I'll just show you guys the trick that I used when I was taking calculus. So basically the way that it shakes out, give me a second to pull up my note. So we got the limit as x tends to 5 from the right. First thing we're going to look at, because clearly the reason that we're assessing the limit at 5 for both of these, we're going to assess it from the right and from the left, is because when we plug in 5 into the denominator, it gives us an irrational answer. And so since we can't use our rationalization techniques, which we will get to in the next section of this recitation, we are going to think about it a little bit more conceptually. And the trick that I use is to just determine what the sign is on top and bottom. So when you plug in 5 to x plus 1, is it positive or is it negative? 5 plus 1 is 6, and so we get a positive answer on top. Just want to double check that this is still screencasting. Yes, okay, good. All right, now, so the numerator is positive, we've determined that. Now what requires a little bit more thinking? But it really doesn't, because the technique I'm showing you is meant to simplify this, because there's a more abstract conceptual way of thinking of it. The way that I've found worked for me when I was taking the course and what's worked for my students is to just break it down into this little trick, because like I mentioned in recitation, though limits are very important for conceptual understanding of calculus, it's not something that you're often going to have to recall in this course until you get to the end, to those all-encompassing problems that are meant to test all the things that you've learned throughout the course. So not that limits exist in a vacuum, but we're kind of going to forget about them for a while. So it's okay to use a trick rather than to understand everything that's going on with this problem. If you are one of those people who tricks don't do it for you and you need to understand what's going on in the background, please come to my office hours or shoot me an email. I would be happy to explain it. But I have found that it often confuses students more to give a long explanation rather than just to show them the trick. And the trick is to think, okay, where does the denominator approach from? The positive side or the negative side? And it approaches from the positive side. And so we put positive in the denominator, and a positive over a positive is going to give us a positive number and positive infinity. And the answer there is positive infinity. Okay, so the limit is x tends to 5 from the right. So same deal here, we're still gonna get 6 in the numerator when we plug in, but if we're approaching from the left, now we have a negative in the denominator, and that makes the whole fraction negative, which makes our infinity negative. And that's the trick, and that's how you do it. Okay, so now we will move on to another graphical problem. This will be the last graphical problem that we do before we move on to algebraic limit assessments and the skills that we use to do that. So sketch the function and use it to determine the values of a for which the limit as x tends to a of f of x exists. So we'll address the second half of the question afterwards. We will just focus on graphing for now. So I have color-coded these just for teaching purposes, not that you would ever be expected to do that. But so I'm going to start with the second line within the piecewise function, the x squared between -1 when x is between -1 and 1. So we know what x squared looks like. It's a parabola, just looks like this. And so we know that it's between -1 and 1. We know how to graph a parabola between -1 and 1. What's 1 squared? 1. -1 squared is 1. So start with what you know is what I'm getting at here. It's going to look something like that. Now, we're going to pay special attention to where the less than and equal to or greater than and equal to signs are, because that is where we know the function values for sure. We can't, so if we're asked to find what the function value of f of -1 is, we have to use x squared, because that is when x is equal to -1. neither of the other two aspects of the piecewise function will give us the correct answer because they don't apply unless within the range -1 to 1, -1 inclusive, 1 not inclusive. So if we were to find f of -1, we would get -1 squared. Use your parentheses, please, please, please. When substituting in, always use your parentheses. I know I said this to both recitations yesterday. There will be at least 5 of you who lose points on the first homework assignment because you make a dumb mistake because you forgot to use parentheses. And it may seem simple and elementary and it might feel like overkill, but I've caught mistakes at my 300, 400 level courses in math that I wouldn't have made if I had just used parentheses. It's as simple as an oversight. So just use the parentheses. You will thank me for it. So f of -1 is -1 squared, which is just equal to 1, like we guessed. But we get to color in this little dot here in blue because we know that this function value belongs to the aspect x squared of this piecewise function. So the next thing that I'm going to do here is I'm going to look at the green part of the function. I'm going to look at 2 minus x. So I know that the function, or I know that at 1, x equal to 1, the function that we need to use is 2 minus x. So if I need to find f of 1, I'm going to, for the sake of organization, just do that really quickly. So if we're going to find f of 1, we've got to use the part of the function where 1 is included in our parameters, where it's equal to. And so f of 1 is going to be 2 minus 1. That's definitely overkill. I personally probably wouldn't have parentheses around that, but I'm going to take my own advice. And the answer here will also be 1. Good, like we expected. However, this function, or this function value, this point here, belongs to the green aspect of the graph. Not that that becomes a huge part of how we're going to answer the second half of the question, where it asks for what a values f of x, or the limit as x tends to a of f of x, for what a values it is true or it exists. Yes, that's not going to be super important in determining that part of the question, but just so we're keeping it clear and so we know how to graph these, because for the third part, the black part of the function, it's not going to line up as perfectly. So if I want to graph the rest of this function, and since I know that it's when x is greater than or equal to 1, I know that this linear function is going to continue on and on and on, and I'm going to write this with an arrow. So the way that I'm going to do this is I'm going to find what f of 2 is, and then all you need to draw a line is 2 points and connect them, and that's how I'm going to do that. So f of 2 is going to be 2 minus 2 equal to 0, so I get a little point there. And that's that. Okay, so now the first aspect, the black aspect of the function. So off the bat, since there is no less than or greater than and equal to, there's no inclusive symbol there, we're not going to have a function value at the end, we're going to have a whole, because this leads all the way up until -1, but it does not include -1. And so we can't write any filled in function value at x is equal to -1 in black for this part of the function. So if we're going to find what f of -1 is, because if we're addressing limits, we're, I shouldn't say. So like I said, we haven't really gotten too much into discontinuity, but your intuition should tell you that you should first start at -1, right? Well, I mean, that's the parameter there, right? So f of -1 is equal to 1 plus -1 equal to 0. But we don't have a function value there, so it's a circle. So then the next value I'll find, and I can tell that this is going to be linear also, and the next value I will find is f of -2, which is 1 plus -2, which is -1. So that goes right there, and we connect the dots. Oops. And that's our graph, and you would get full points for a graph like that in one color. You wouldn't have to do multiple colors to make it clear which function belongs where. What you would lose points on is if you were to fill in this hole here, you would lose points for not having it line up with your parameters. But now we get to the second half of the question, and it asks, use it to determine the values of a for which the limit as x tends to a of f of s x exists. So remember earlier, I asked you guys to find the limit for this one here as x tends to 1 and it's just equal to 2. So wherever there's a function value, the limit exists, basically. And so for this particular question, the limit exists everywhere except for right here. Reason being that the limit from the left, says my screen sharing is paused. Okay, good. All right, the reason being that the limit from the left is not equal to the limit from the right. If we're asked to assess the limit from the left here, we would approach and find that the limit is 0. If we were asked to assess the limit from the right of the same function, we need to remember that f of x all of these aspects belong to one function. If we approach from the right, we get that the answer is 1. And if the limit from the left is not equal to the limit from the right, then the limit does not exist. And so for what a values does the limit as x tends to a of f of x exist? It exists for all values of a except for a equal to -1. And you will find that answer written out in my recitation lesson plan note that was sent to you via email. All right, moving on. Evaluate the limit if it exists. So now we're getting into our algebraic applications. So the limit as x tends to 5. In general, there's kind of two big skills that you're going to use. There's kind of the blanket term, algebraic manipulation, and then there is the conjugate. The conjugate is going to be the last thing that we get to, and it's going to be the big skill that you learn for limits. It's going to be kind of the big guns, I think I've called it a couple times. When you're doing algebraic manipulation, more often than not, it's going to be to factor or to FOIL, condense or expand, or it could be to simplify, combine like terms, whatever it may be. But what we notice here is that when we plug in 5, we get something irrational in the bottom. So what do we have to do? We have to rationalize it. And how do we do that? We use one of our rationalization techniques, algebra or the conjugate. So in this case, the numerator is begging to be factored. You will start to, if this doesn't scream factoring to you, you will start to get a little bit more intuition for it. But you will also be able to, like I said, in your arsenal, you've got 2 skills for rationalization. You've got the conjugate and you've got factoring, or not factoring, excuse me, algebraic manipulation. The conjugate has a very specific, like I said, this screams to be factored. Problems that need the conjugate scream to use the conjugate. And it'll be very obvious when you're supposed to use the conjugate. So if it's not obvious to you that you're supposed to use the conjugate, and I'll talk about why. Okay. I'm really hoping that it didn't not record my entire explanation of the graph there, because I had my Notability open so I could reference my notes while I did it. So I'm really hoping that you guys caught all of that, but if not, you at least heard my verbal explanation of it, and you should be able to follow along with the note itself. So I apologize if this doesn't show up on the recording, and I will leave my note now as not to mess with the recording in the future. Okay. So the limit as x tends to 5, like I said, we're going to have to use a rationalization technique. It'll be more clear to you after we do a problem at the end of this recording when to use the conjugate. And if you don't use the conjugate, if using the conjugate isn't what's required in that situation, then you got to turn to algebra. And so for this particular problem, to me, it looks like it needs to be factored. And when we do that, we get the limit as x tends to 5 of x, I believe it's x minus 6, let me double check. Nope, x minus 5, x minus 1. If you aren't up to par on your factoring, watch a Khan Academy video. I still brush up on factoring every now and again, just because sometimes I don't know, a little brain fart here and there. But factoring, I feel like, is one of those skills that makes sense once it's been re-explained. But if you were to be asked to take a quiz right now and asked to factor something, some of you might struggle just because you haven't seen it in a while. So I would recommend watching a video on that. So now in the denominator, we maintain that x minus 5. I want to make another side note. So earlier I said one of the most important things you should take away from this recitation is that if the limit from the left does not equal the limit from the right, then the limit itself does not exist. Secondary to that, and I'll also throw in substituting with parentheses, that's also very important, but I'll say that that's third. Second is that you do not drop the limit symbols, the limit as x tends to 5. You don't drop that until the very end when you plug in. And we'll see what that looks like in a second. But you need to rewrite it. It might feel tedious, but you rewrite it until you finally plug in that 5 for x at the very end. So these problems, like I said, they are engineered to test you on these. And so more often than not, you'll get something nice like this where your terms will cancel, because that's the intent. That's how they want you to rationalize it. They want you to factor it so that one of the factors can cancel with the denominator, and it'll take out that x minus 5 so that when you plug in the 5, it's no longer irrational and you no longer have a 0 in the denominator. And so now what we have, I'm still rewriting my limit symbol is a limit as x tends to 5 of x minus 1. Now I get to drop the limit symbol because I'm plugging in. I get 5 minus 1 is equal to 4, and we have just found a finite limit using a rationalization technique using algebra. Okay, and now we will do another one that is practically the same approach. So we get the limit as x tends to 5 of, I think this one's x minus 6, let's double check. Nope. X minus 3 and x minus 2 over x minus 5. So this one doesn't work out quite as pretty. It doesn't cancel, and we're not able to rationalize it with any of the techniques that we know. We have not yet looked at a conjugate problem, but once you see the conjugate problem, it'll be obvious to you that this is not a problem where you can use the conjugate. The only sort of algebraic manipulation that would be called for in this situation would be to factor it, and then thinking ahead, you would know that it would have to cancel in order for it to rationalize. But in this particular case, the problem was not set up to do that. Why? Because they want you to understand that in this case, the limit does not exist. It's irrational. It doesn't exist. Sometimes that is the answer. Even after you do the manipulation and you've done all the work, sometimes it still just doesn't exist. Okay, the limit as t, this one didn't get erased, but I'll just kind of go over it. So I mentioned in recitation that this one was worth noting because it's a difference of squares, and I think that it's beneficial to kind of point out those sort of patterns. When you see, so like this might not look like something that's screaming to be factored, but if you know what a difference of squares is, t is squared, 3 is squared, t squared, minus 9, minus being the difference, then you can recognize that this is easily factorable. So we get t plus 3, t minus 3. We also factor the denominator. Again, I would recommend watching a Khan Academy video if looking at this is kind of daunting, thinking of how you might factor that. Because honestly, for me, if I were doing this on the whiteboard for the first time and never had looked at it on my own, it probably would stress me out a little bit too. So I really recommend watching a Khan Academy video as to factoring, because factoring is one skill that we will continue to use throughout the semester. But we cancel the t plus 3 term in top and bottom, and then when we plug in with parentheses, we get 6/5, and that's that. So number 17 is another similar problem. So now what we're going to do rather than factoring is we're going to FOIL out, we're going to expand. So we get the limit as h tends to 0 of 25 plus h squared minus 10h minus 25. So I'm going to double check that. Yep, all over h. So h is a variable that we will come to associate with the definition of the derivative, which we have not yet discussed. But like I mentioned with positive and negative, it's standard convention to see x and y. Get comfortable seeing other variables, because we will throw them, like the textbook will change up the variable every other problem on you just to get you comfortable with the idea that variables are what you make them. So just because you see h in the future does not mean that we are doing a definition of the derivative problem. I know you guys don't know what those are yet. Basically what I'm trying to say to you guys is just because you see something that looks familiar to, like if you see a variable, that one variable doesn't mean that you're being tested on one particular concept. We're going to pull those variables from all the concepts so that you don't get comfortable in identifying a type of problem based off of the letter variable that we use. I'm not saying that's exactly why we do it, but that is what we do. So 25 minus 25, those two are going to cancel. We are going to divide an h out of h squared, just going to get h, and negative 10h, we're going to get negative 10. So when we simplify, we get the limit as h tends to 0 of h minus 10. And when we plug in, we get 0 minus 10, which is negative 10. And that's that. So that was the last of the algebraic manipulation examples. That is not the extent of the algebra that you will need to know for this course. I would recommend looking at some of the other examples in the book. I didn't grab the most complicated examples for our recitation, but that being said, Dr. Zlecki probably will not grab the most complicated examples for your quizzes and exams either. So as long as you feel comfortable with the problems that have been presented to you via WebAssign and in recitation, you should probably be good as far as algebra goes. You don't have to go searching for the most complicated versions of these problems to feel prepared, because Dr. Zlecki, as a general rule of thumb, he's not one to try to trip you up or make things more difficult than they have to be. He wants to know what you know. Okay, so like I said, that was the last of the algebraic problems. Algebraic manipulations, not that this still isn't technically an algebraic manipulation, but as a rationalization technique, now we are moving into the conjugate. So we're only going to do one example of the conjugate because we will get more practice in the future. Like I said, this is the big gun. This is the thing that we will come back to the most when we're working on limits for rationalization, because it's really the only technique that you're learning. Because algebra at this point, though you may not be used to applying it in this context, that's not a new technique to factor or to FOIL. So this is the one that we will probably spend the most time on. I do not know if Dr. Zlecki has spent much time in lecture on his own yet, but this is something that we do spend a little bit more time on in my experience compared to the rest of the limit unit. So the conjugate. I told you earlier that factoring problems scream to be factored. The conjugate screams to be conjugated. I actually don't think that that's the correct verb for that. But when you're using the conjugate, you're essentially multiplying the phrase by 1. The reason for that is you're going to multiply it by a fraction that's the same in the numerator and same in the denominator. So I'm saying that to make it clear to you guys that we are rationalizing. We're putting this in a form that is workable for our purposes for the scope of this course. We are not changing the equation or the phrase by any means. We are just putting it in a form that works for us. So the part about this phrase here that screams at us to use the conjugate is that we have a radical symbol here. We have a two-term phrase underneath the radicand, and we have another number. So it's entirely possible that that could be a fraction. In this case, it's an integer. We will more often than not see an integer, but just because if you see a fraction in the future, that doesn't mean that it's not the conjugate. If you see something that's underneath the square root and then plus or minus another number, that means you're probably going to use the conjugate. And when you use the conjugate, you are essentially going to rewrite the numerator, 9 plus h, but you're going to change the adjoining symbol. So square root of 9 plus h plus 3 in this case. And the reason we do that is because we want things to cancel out. And you'll see what that looks like later on. So now we are going to FOIL out. We get the limit as h tends to 0. I'm not dropping that limit symbol. So we're going to have square root of 9 plus h squared plus negative 3 times positive 3 all over h times square root of 9 plus h plus 3. Now, I am going to expand the numerator. I am not going to expand the denominator. The reason for that being that I have done these problems enough, and it won't take you long for you guys to have this intuition as well, to know that if I try to simplify or if I try to distribute that h out in the denominator, I'm just going to end up having to undo it for the purposes of this problem, because like in the earlier problems, we want things to cancel out in order to rationalize. And for the conjugate, when you're using the conjugate, basically at this step, leave the denominator alone. If you forget and you do manipulations in the denominator, that's fine. You just might end up confusing yourself because you're gonna have to undo those manipulations in order to get to the correct answer in the end. So the limit is h tends to 0. When you square anything underneath the square root, it's just what's under the radicand. not dropping that limit symbol. Limit as h tends to 0. We get 9 plus h minus 9 over, and I'm going to maintain this whole thing here. Okay, so now, once again, we get some handy canceling. And we get the limit as h tends to 0 of h over all this noise. So once again, we get some canceling. And that's why I didn't want you guys to FOIL out the denominator. We don't want, I mean, it would have been fine in this particular case because all it would have looked like is h square root 9 plus h plus 3h. And you'll probably be able to just think that out and not have to undo those steps. But in some problems, it gets a little bit more complicated. Like I said, if you do forget and you manipulate the denominator, it's fine. You can always backtrack. But in general, you're just giving yourself more work in doing so. So now we have the limit as h tends to 0 of 1 over the square root of 9 plus h plus 3. So we've still got an h in the denominator. But now when we plug in, it's rational. And that's all we want out of this. You don't have to get rid of all of the variables in the denominator. That's not the end goal here. The end goal is to come up with a rational answer. And if you plug in 0, in this case, you will get a rational answer. And since I'm plugging in, I'm going to drop the limit symbols. And it's just going to be 1 over the square root of 9 plus 0 plus 3, which is 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is 1/6. And that's the conjugate. So in office hours tomorrow, I would absolutely do some more of these problems since we didn't do too many of them in recitation. Like I said, I would expect us to do more of them next week. As always, feel free to email me with any questions you may have about the recitation material or about the course itself. All right, I'll see you guys next week.